So we're looking to solve this integral x squared plus 1 over x cubed minus x squared. And we're going to end up using something called the method of partial fraction decomposition. And to do that, the first thing you want to do is factor your denominator. I can pull an x squared out of these two terms, and then I get left with x minus 1. So we want to rewrite this as the sum of two or more fractions. And there's a certain way we have to do this because we have what's called a repeated root. X is a factor that's repeated twice. So a linear factor that's repeated twice, we need to represent that. So when we go to rewrite this, we can write a over just the linear factor of x, but then I'm going to have to put something over the repeated factor. And if this had been an x cubed, I would do c over x cubed, so on and so forth. So you do that for any repeated factor. Now for x minus 1, we'll have c over x minus 1 dx. And now we need to create our system. The way we do this is we're going to multiply a, b, and c by whatever factors we need to get this common denominator. Currently a has a denominator of just x, so it would need to get multiplied by another x and x minus 1 to have this common denominator. So a times x minus 1. B already has x squared, so this term here only needs to get multiplied by x minus 1. And c has the x minus 1 but not the x squared, so that term would need to get multiplied by x squared in order to ensure a common denominator. Now this, I don't worry about the denominator because I know that these are going to be the same. This is the numerator if I were adding these three fractions together with a common denominator, and I want it to be equal to x squared plus 1. Sometimes you have the option of canceling out and solving, but you can see if we use 0, we have two terms that cancel out, and if we have 1, we have two terms that cancel out. So I'm going to show you another way of doing this, and that involves actually multiplying this all out and seeing what we get. So distributing this, we end up with ax squared minus ax plus bx minus b plus cx squared equals x squared plus 1. Now there's several different ways to do it at this point. One of the things I've always enjoyed doing is grouping my terms by what they're being multiplied by. So I'm basically grouping my coefficients. I'm going to group them for x squared, x to the first, and x to the 0. So I'm not actually going to put x's in my equations, but x squared, notice, has to have a positive a and a positive c. So a plus c, and over here x squared has a coefficient of 1, so a plus c must equal 1. For the x to the first, I have a minus a and a positive b, but there is no x to the first term over here, so that must equal 0. Finally, my constant term, the only thing I got over here is negative b, and that must equal 1. And we have enough information now to go ahead and solve this. So b, if negative b equals 1, b has to be equal to negative 1. So b has to equal negative 1. Right here, because negative a plus b has to equal 0, we get from this equation that a must equal b. So a has to be negative 1. And now a plus c has to equal 1. Well, negative 1 plus c must equal 1 gives us that c has to be 2. So a pretty easy system to solve for this one. And now we can put together our integral. So we have negative 1 over x minus 1 over x squared plus 2 over x minus 1 dx. And we'll do all these separately. Now this one is pretty straightforward. It's just negative ln of the absolute value of x. Now what I'll see here is I'll see a lot of people really quickly say, oh, well, that's just negative ln of x squared. Remember, this is the same thing as x to the minus 2. This is not the derivative of natural log of x. This is just a power rule. And what we would get is x to the negative 1 over negative 1. So we're going to end up with plus 1 over x. And if you're not sure, take the derivative of that. You'll get back to this. And this one, again, we do have an ln. So plus 2 natural log of the absolute value of x minus 1 plus c. We could, if we want, combine these natural logs. And what that would look like, we have 1 over x. First, we'd have to put this 2 back up in the exponent. And then we can drop the absolute value because that 2 will make it be positive. So x minus 1 squared, oops, that should be plus there, minus ln of the absolute value of x plus c. Now because we have a difference of natural logs, we can combine those. So we have 1 over x plus natural log of x minus 1 squared over x. And there's our absolute value plus c. There's our antiderivative.